you did. Did you get 4 for the first one? Now, you could have done 4 times 3 times 2 times 1 and got 24 on the top, and 3 times 2 times 1 and got 6 on the bottom. But I think it's a lot easier to notice that the 3's would simplify, the 2's would simplify, and when they simplify, they all turn into 1 over 1, so you just get 4. Same thing with the second one. Can you see 4's will simplify, 3's will simplify, you're just left with 6 times 5, which is 30. And in the last one, 5's, 4's, 3's, 2's, 1's would simplify, and you're left with 8 times 7 times 6. This one is a little bit harder to do the mental math, but you should have got 336. 6 times 50 is 300. 6 times 6 is 36. Add them together, 336. Here's a counting question. There are 4 ferry routes from Vancouver to Vancouver Island. You want to travel from Vancouver Island by 1 ferry route, but make sure you come back on a different one. How many ways could that be? Now this is connected to what we were doing last class, when we could count things like how many subs does Subway have. No, not yet. You didn't enjoy it. No,
you still want me to? You're like, I'm serious. Give me an extra 5 marks.
So the idea of those were we made a space for every decision that needed to be made, and then in each space, in each decision, you wrote down how many choices you had. So if you're traveling from Vancouver to Vancouver Island and back, you have 2 decisions to make. Decision number 1 is getting there. Decision number 2 is getting back. So I could describe, just like as a little description underneath each of those decisions. Vancouver to Vancouver Island would be my first decision, and then I got to decide on how many ways that I come back. Now normally there would be 16 in total, 4 ways there, 4 on the way back. But you're supposed to take a different route on the way back. So choices on the way there, you could take any 4 routes on the way there. But if you have to take a different route back, how many choices do we now have? 3, which gives us 12. If a 5th route was added, can you see that it would be 5 and then 4? If a 6th one, it would be 6 and then 5. And so we're multiplying them out, just like we did at the beginning with the fundamental counting principle. So the fundamental counting principle will keep coming back, but this time our choices decreased by 1 because we were told we had to take a different route back. Okay. Now, something new that we're going to learn today, a new mathematical symbol that you've never seen before, perhaps, well, you've probably seen it before, but maybe not in math. The exclamation mark. So, what happens when you have 1? Okay? You actually don't, technically you read it as 1 factorial, but it kind of looks like, in English when you put an exclamation mark, you just have to be excited about something. It kind of looks like 1. But 1, an excited number 1, is not that exciting actually. It's just equal to 1. And 2 is just 2. But 3 is 6. And 4 is 24. Can you figure out what 5 is? Do you see a pattern? figure out with 5 factorial, 5 with an exclamation mark, what it's actually equal to. 120. And how did you find the 120 given? Right? You took this one and you multiplied it by 5. So 6 would be taking this last one, whoa, and making the whole screen disappear. This is wonderful. There we go, we're back. Making the whole screen disappear, but we're back now, and multiplying this by 6 would give us 720. And so the definition, if 6 is just 5 factorial times 6, and 5 factorial is just 4 factorial times 5, and this one you got from here by multiplying by 4, and here you multiplied by 3, and here you multiplied by 2, then 6 factorial is just 6 times 5 factorial, and 5 factorial is just 5 times 4 factorial, and 4 factorial is just 4 times 3 factorial, and 3 factorial is just 3 times 2 factorial, and 2 factorial is just 2 times 1. So the factorial sign is a shortcut for starting with that number and multiplying every number down to 1. And it comes up enough in mathematics that they made a sign for it. So if you had, and the numbers get very big very quickly. Like 7 factorial is already 5,040. 8 factorial is already over 30,000. So the numbers get very big very, very quickly. In fact, our warm-up, this one was actually 4 factorial divided by 3 factorial. The second one was actually 6 factorial divided by 4 factorial. And the last one was 8 factorial divided by 5 factorial. And we're going to figure out that sometimes questions like this one, 4 times 3, is actually 4 factorial divided by 2 factorial. And where those things come into play and how we can use them to solve equations. So what we have here, if you had a word like Kelowna, and you decided, I love the city of Kelowna, I'm going to make my password Kelowna. And then someone says, I know what your password is, and you're like, okay, then I'm just going to take the letters of Kelowna and mix them up and make a new word. Like, I don't know, what would be a nice new word that we could, Wolanek. No. There we go. That will be my new password from now on. Wolanek. Very catchy word. I can remember it. Nobody will ever guess it. Except for you guys who watch this video. Break into my online banking now. So the question is, if you had the letters of Kelowna, how many different passwords could I have made? Well, there would have been 7 decisions because there's 7 letters. And then I have to decide which letter is first, which would give me 7 choices. But now, one of the letters, like if I chose the W, one of the letters is gone. And now I only have 6 choices, then 5, then 4, then 3, then 2, then 1, which is the same as 7 factorial. So when we are rearranging things, and you're not allowed to repeat something or use it again, that is called a permutation. So what we just figured out was how many permutations are there of the word Kelowna. There would be 7 factorial, or 5,000. 5,040. And so we have to know our factorial notation, and this is still a number even though it doesn't follow the normal definition. The normal definition says whatever number factorial, you just keep going down by 1 until you get to 1. So if I took 4 factorial, it's 4 times 3 times 2 times 1. 10 factorial, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 850 factorial? No. But it just keeps going down to 1. But this, if you start at 0, you can't go down to 1. So this is its own definition. For some mathematical formulas to work, 0 factorial is equal to 1. It doesn't make sense with the regular definition. It looks weird. It's just a definition that you need to know. We'll show why it has to be in some of our formulas, and we'll explain why the definition of 0 factorial has to be equal to 1, but it doesn't make sense according to the regular formula, which means just go down by 1 until you get to 1. All right, let's go to example 1.
Oh.
Yeah. Well, we're going to play some fun word games today. Make you think hard. Maybe even give you a headache. I don't know. Okay. Here we go. First word puzzle is we have the letters to the word education. If you wanted to make different arrangements of the letters for education, there's 9 letters in total. And if you wanted to figure out how many different words you could make, you could do 9 spaces. 9, 8, 7, 6, 5, 4, 3, 2, 1. You could put any letter first. Any letter, then you've used up a letter, so now there's only 8 choices for the next letter. Does it make sense why it goes down by 1 each time? And the number of rearrangements of the letters from the word education ends up being 9 factorial. You know what's cool about the word education? It has all 5 vowels in it. Can you think of any other words that have all 5 vowels in it? There is apparently a 1-cell biology thing that they named just with 5 vowels. It's apparently a word. But there are other English words that have all 5 vowels. There is a tree that has only 7 letters and has all 5 vowels. Can you figure out what kind of tree it is? This first word. I told you I'm going to give you word puzzles that are going to cause you to have headaches today. I'll tell you the answer to the tree problem in a bit. I just want to give you more puzzles. We don't do puzzles? Oh, we should do that. We should do that. All right, questions for practice on this one. 3, 5, and 9. Another puzzle. Can you think of an English word that starts with he, H-E, and the word ends with he, H-E, but isn't he, or he, or he, or any he words? And to make it worse for this puzzle, I've already used this word twice in my lesson today, in the last 3 minutes. Okay, you can work on questions 3, 5, and 9.